All right. Always a pleasure to speak at Midas events. Very well organized and very excited to share a little bit about this. This might be uh, the third time I'm giving this talk in this venue, but every time there's a new angle to this, which I think for me is very very enriching to tell you the story. Uh, and so the goal of this work was to try and develop one foundation model that essentially can reason across all of chemistry. That was sort of the, sounds grandiose, but that was the goal, and I think we're making some good progress on that front. So let me start by sort of asking what the definition of the problem statement that we're thinking about, and then I'll tell you a little bit about the methods that we've used to address this. Chemical space, right, is vast and really, really important in nearly everything that we use and touch and feel. Small molecules, right? So that is an important part of life. It's important in therapeutics, drug discovery. It's also important in energy applications. Then you have organometallic complexes. So these have organic ligands, but also a metal center, and large portion of biology also functions with sort of these metal centers, right? Hemoglobin being one of the important ones, where the iron center binds oxygen, and it's the geometry that sort of enables this functionality. And then, of course, important things happen with isotopic effects, and radioisotopes and therapeutics, all play a big role. And then finally, one thing that is extremely important from a industrial standpoint is formulations. And formulations is when you take these molecules and then mix them in different ratios, right? And I think that defines a lot of different domains, right? Defines energy applications like batteries, defines lubricants, paints, right, etc. So it's a large body of things that can be achieved with this. And so the goal is to build a model that can one model that you can then fine tune for a number of these downstream tasks and be able to sort of demonstrate incredible performance across all these things. And so that's the sort of agenda for today. And so I'll tell you a little bit about sort of our work, our journey over the last about 3 years or so building this. And we've learned a lot, and we'll show you sort of where we are. Okay, so the starting point is, why do we believe that chemistry is primed for these foundation models? And the idea starts from this sort of picture. So if you look at any reasonable guess of what the size of the chemical space is, so you can sort of many estimates, but it's sort of order very large number, right? 10 to the 60 is sort of one estimate. And if you look at the space of what has been explored, for example, in drug discovery, like it's sort of order maybe 10 to the 4, 10 to the 5 molecules, and then in energy applications, which I come from, right, it's of order about 1,000. So the number of labeled data sets is very, very small compared to the size of the chemical space. Okay, so which means that you have to sort of look for methods that go beyond that. Now, if you ask what is the space of unlabeled data sets, that actually gets much more interesting. So there's a lot of unlabeled data sets. This means that this basically just is a molecule representation that one can synthesize, for example. And there's a lot of much larger data set of these unlabeled molecules. Enamine Rio being sort of one of the largest ones. Actually, this is already out of date, 50 billion. Now it's 80 billion. Enamine Real is a data set of molecules that Enamine thinks it can make in a short notice to you and deliver to you. So basically, it's synthetically accessible molecules. And so the idea that we had was the following, which is that you have this vast chemical space, and so you have all these unlabeled data sets. So can we do pre-training in the same way that traditional language models have been pre-trained on, right, like internet text and others? Can we pre-train on these large corpus, which then you fine-tune for trying to predict properties of various kinds of molecules and materials? And so that was the core thesis that we went after. And I'll tell you a little bit about this in sort of along various fronts. So the first part will be sort of much more computer science heavy, and then the second part which will be much more sort of chemistry heavy in terms of what we have done. Okay, so first is, what's sort of the language of molecules in chemistry, and so here we benefit from something that was discovered or invented in 1987, which is how do you represent a molecule in the form of text. And so here is an example molecule, right? And the way this gets represented as a simple text is first you break these rings. So you break these three rings, and then you do sort of a depth first traversal. So you basically find the longest chain, and then you sort of bifurcate, and then you write this in what's called a Smiles representation. And so the Smiles representation essentially is a string representation. So this is a 1D string that essentially can be used to map back into this 2D structure. Right? So essentially, you have a 1D representation that now starts to look like language, right? And so the beauty here is now, essentially, you have a language that you can now tokenize, and then you can use all the machinery that's been developed for large language models, but now in the context of chemistry. Okay. And so the goal of our work was to build this model called MIST, and I'll walk you through the left side because this is sort of the core idea of sort of how it works, and then I'll tell you a little bit about what we did uniquely. So this is a molecule called cisplatin. Okay, this is a cancer therapeutic, and it's important that it's cis and not trans, because trans is not a therapeutic. Okay, and so here, right, so you have the two chlorine moieties on the same side, and then the ammonia on the other side. Okay, and that then gets represented in this text form like this, right? So you have this at sp1, right, which sort of says the square planar geometry. And what we had to do along the way is we had to come up with a new tokenizer that handles chemistry well. And I'll tell you a little bit about the difficulty of needing a tokenizer that can do this properly. So if you notice what's happening, right, so naively, right, tokens are basically a way in which a language model, right, it's a vector representation, right, that a language model can understand, right, that this is a token, right? So any block that you think is a moiety of that grammar, right, you want to sort of assign it a token. Now, for chemistry, this becomes interesting because you can naively say, well, I can assign chlorine as a token, platinum as a token, ammonia as a token, or N as a token, H as a token 3. But then you see these interesting things of what happens inside the brackets. Right? And what happens inside the bracket is attributes around whatever is happening with the geometry. So for example, here, right, you have platinum at sp1, right? So which means that this is platinum with a square planar complex. Now, this can be any combination, right? Square planar, it could be octahedral, tetrahedral. And if you start to categorize every one of them as a separate token, right, then your grammar explodes, right? Because then basically you have combinatorial complexity of basically mixing all kinds of things. And so what you want to do is break all of these down. And so the previous tokenizer that was the state of the art was a regex tokenizer called atom pair encoding, atom pair tokenizer. So what it does is basically takes this and then breaks this down. But what they did not do was to further break out what's happening inside the brackets. And that turns out to be very important, as I'll talk to in a little bit. And once you break that down, then every one of these moieties becomes an independent token. And that then gets fed into our language model. So this tokenizer is Merck, and I'll tell you a little bit more about the attributes of what we have done here that allows us to do some interesting things. Okay, so you have a molecule, then that gets tokenized through this Merck tokenizer, and then MIST is an encoder-only model. So basically, it takes this molecule and then creates a vector out of it, and then that vector can then be used to do supervised fine-tuning, and then pre-training. And so the pre-training, the way we do it is we have this sort of large corpus of unlabeled molecules, and we do mask language modeling, right, which is we mask some number of tokens and we ask it to predict the missing tokens. Okay, so actually, I have been intimately familiar with this line of work for a long time, and stayed away from it. And I'll tell you a little bit about the history of this and how I sort of corrected my own thinking here. So the earliest language foundation model was Kimberda 1. It was built by one of my close collaborators, Bharat Ramsundar, in 2020. And one of the first things I told him was, why are you wasting your time? Right? This is never going to work, right? Because naively, it seems absolutely absurd that you have a molecule, right? And a molecule fundamentally, right, has nodes and edges, and graph seems to be the right language to represent molecules. Okay, and so we were obviously down the path of building graph neural networks with either graph convolution or various kinds of message passing, and so it seemed like this trajectory was a futile trajectory, which was true, right? So the very first Kimberda models were terrible compared to any graph-based model. Okay, so they were just awful. Now, what happened in the next 2 to 3 years changed my perspective. So Kimberda 1, and then they built Kimberda 2, which is essentially, roughly speaking, right, there's all this sort of nuances around, there's some minor changes around, like, rotary position embedding, rotary position encoding and stuff like that. But, highest order, there are only two things that changed, right? The size of the molecules that they pre-trained on and the model size. So it went from something that was pre-trained on order 10 million molecules to something that was pre-trained on about 70 million molecules. Okay, and then of course a couple of orders of magnitude improvement in size. And suddenly you started to see these scaling laws emerge. So you started to see that the models got systematically better and better. And then IBM, around the same time, right, came out with Moleformer XL, which was pre-trained on about a billion molecules. And then you suddenly started to see extremely competitive performance by these pre-trained language models compared to graph-based models. So around that time, we took a bet that essentially, it seems like the scaling laws are allowing you to sort of have the superhuman reasoning around chemistry. So could we just scale this up dramatically? And so we've trained a family of models, MIS 25, 228, and 1.8 billion, and all of these models, trade off different levels of performance, time, and accuracy. But the 1.8 billion model, right, is essentially at this point really incredible and state of the art across essentially almost all tasks, except for a small number of tasks where having the three-dimensional geometry information is useful. Other than that, essentially for all tasks, these models, the pre-training really, really helps. And then when you fine-tune on a small data set, you really have extraordinary performance. And so, over time, I have sort of changed my viewpoint. And I think there's a lot to learn around scaling laws in domain sciences. And I'll tell you a little bit about our journey in this process. We're early on, but I think there's a lot of interesting things to do here. Okay, so I'm just, I think the audience is sort of very diverse. Some that are experts in computer science, some that are expert in the domain. So I'm going to just walk you through a couple of core ideas. So one of the core ideas of these scaling laws emerged. The original idea was first proposed by Jared Kaplan, when he was at OpenAI and then at Anthropic. And the core idea is the following. So the validation loss, for example, of your pre-training depends on two things, right? Depends on the data set size and depends on the model size. Okay, so model size being n here, data set size being d here. And what they argue is that it has to have this power law behavior, right, which is a over n to the alpha, b over d to the beta, where alpha and beta are scaling exponents. Okay, and the reason for this is as n tends to infinity, if the number of parameters tends to infinity, all you have is the loss associated with your inefficiency with data. And then in the limit that you have unlimited parameters and unlimited data, right, you basically will converge to whatever is the fundamental entropy of that particular problem statement that you have, right? So there's some fundamental entropy that, the next token is not deterministically any one token, but there's some, fundamental entropy associated with that. Okay, so the core idea here is as you scale number of parameters and number of data, and you need to do this in an efficient way, right, then you essentially have a predictable way in which you can come down the loss. Now, the compute required scales sort of roughly linearly with the number of parameters and number of data, right? So which means that now you have a very simple problem statement where you want to minimize the loss subject to the fact that I have certain compute budget. So that then gets you an optimal number of optimal scaling of the model with respect to the data set, which comes out as the exponent beta over alpha. And what this allows you to do is get you a compute optimal frontier. And in order to do this, we added one minor twist from this particular work. And the core idea here is this assumes that everything else about your model is perfect, right? But when you do a normal training run, you have lots of things, right? You have learning rates, you have feed-forward ratios, you have all sorts of attributes of the model. And so that ends up being important. And so we incorporated that as additional sort of hyperparameter penalties from the scaling law. Okay, and so this is, I forget, maybe like order 100 models that were trained on due to an NSF National AI Research Resource NIRE grant, where NVIDIA DGX cloud was in the hands of my then graduate student Alex Waddell for close to several months. So he basically trained all these models to produce this scaling law. Right. Essentially, what you see is this is validation loss on the contour plot, and then compute budget, right? And essentially, you now have all of these data points, and then these stars are what we are the flagship model. So we ended up training at the very end. What I'm going to talk about next is a couple of attributes that we saw from this training run. So the plot of loss versus compute budget. So it decays as a power law, as I showed you last, right? And then eventually will converge to this E, which is the fundamental entropy, right? That's what the loss will converge to. The rate at which this converges, right, goes as alpha beta over alpha plus beta, which is maximized when alpha equal to beta. Right? So when alpha over beta or alpha equal to beta, that's when this loss is rapidly converging. Okay. All right. So what I'm going to show you on the right, just focus on the right part of this plot. Right. This is data over model scaling. So this is this alpha over beta. And first, actually, before you look at this probability distribution, just focus on this this red curve and then this pink curve. And what you see here is this red curve was an early DeepSeek model, and that was sort of around 1.3 or so. And then they improved the sort of data set, and then they got close to 1. And essentially now all language models are nearly at this perfect frontier of equal to beta. Okay. Now, our molecular foundation model has an alpha or beta that's sort of around 1.6, 1.7 or so. Okay, what this suggests is that the data set that we have, right, is not giving us as much bang for the buck in terms of scaling, right, as the model is giving, which means that there's some part of the data that is essentially redundant. Okay. This is not surprising, in hindsight, because enamine Rio is a data set that was generated, right, through some deterministic rules of how they can synthesize these molecules. Right. So they know that they can put this methyl group here, or the sort of synthetic rules, and so this suggests that the data set can be improved further. And I think there's in the sciences there's an important direction around sort of diversity of data sets and the ability to sort of generate these so-called foundational data sets that allow you to sort of have optimal training. One other point I'll note here, right? So as I mentioned earlier, so we are in this we're in this limit where the data set is the problem, and you can estimate the dimension in which the data set lives in through this sort of analysis of the size of the data manifold. And what this suggests is sort of the dimensionality of the chemistry data set that we have is order dimension sort of 7. And what we believe is to be true is probably the dimensionality in which the chemical space lives is actually much higher. And so there's some interesting opportunity around being able to sort of create better foundational data sets. Okay, so that's a lot of work on sort of the scaling laws and training these models. So we've trained now this sort of very large pre-trained foundation model missed. And so the goal is now to try and put that to use for sort of a bunch of downstream tasks. And so in order to do that, right, so, as I mentioned earlier, right, so we needed to do this one key addition, which is this tokenizer. So this is cisplatin again. And the key difference between sort of what traditional tokenizers do and what SMRC does, so Atomwise, which is at that point essentially the tokenizer used in all the other foundation models that I showed, right, including IBM's Molformer XL. What it does in the middle is you see that it sort of tokenizes chlorine. Chlorine puts unknown, unknown, right? And the unknown, unknown comes from what's happening inside the bracket, right? So it drops the sort of platinum at sp1 because it's not there in the vocabulary. What we do is basically we do another regular expression on that. So it, of course, platinum is in the vocabulary, at sp is in the vocabulary. Every one of these things is in the vocabulary. Now, it turns out that SMRC is important, right? So for the chemists in the audience, right? So, it's very, very critical because what's happening inside the brackets is all of the exciting action. So what's happening inside the bracket has like things like chirality, it has non-bounded interactions, it has stereoisomers, so all kinds of attributes, and these are very, very important in sort of variety of things, right? So things like vitamin B12, right, where stereochemistry is important, fluorodeoxyglucose, where the isotopic effects is important, lithium iron phosphate is a battery cathode, which ends up being pretty critical. One thing I want to sort of point out is the concern around benchmark hacking. So you look at all of these tokenizers here, and you see actually something very, very interesting, right? That if you look at their score on this pink chart, right, they all actually do very, very well, right? What's showing here is the coverage of that tokenizer for these different data sets. And the reason they all do very well on this pink is a very popular benchmark called MoleculeNet. And so all tokenizers make sure that they tokenize everything in MoleculeNet, but they end up not knowing, fairly trivial things, right? Like many tokenizers don't even know all the elements, right? Or, nearly all tokenizers don't know how to handle chirality and stuff. So I think this sort of shows that, benchmark demonstration does not always sort of give you true performance. And SMRC and SMRC GPE, SMRC GPE is just basically creating a glyph pair encoding. So SMRC now extends, because of the fact that we do this additional regex, right, the number of tokens now increases. And so the number of tokens increases makes the model prediction task much harder. And so we created a second version which sort of creates, some glyph pairs so that it brings down the size of the average length of the tokens needed for predicting a molecule. So what this now allows us to do is to sort of push this for a number of downstream tasks to predict, how the foundation model performs for a variety of tasks. Okay, so as I mentioned earlier, right, the opportunity space is vast. You can use this for energy storage. We've used this for we've not used it for fragrances, but we've used it to predict the problem of smell, which then can be used for fragrances. Obviously, very useful for designing lubricants, so predicting dynamic viscosity, paints, and so on and so forth. Okay, so I'm going to show you some examples of what we have done with the foundation model that gives you sort of vignettes of what is the capability once you have this sort of very powerful representation of a molecular space, what you can do with that. Okay, so the first task that we did was something that was sort of in my domain, right? So which is, can we use this to find better electrolyte solvents? So an electrolyte, you probably are familiar with sort of standard electrolytes, right? Like Gatorade, right? So which is basically water and salt, right? So essentially any electrolyte has two attributes. So there's some solvent, and then there's a salt that's inside the medium. Now, when you want to use this for what happens inside a battery, then you have to have other attributes that you care about. So you want to have lots and lots of properties. So an electrolyte must have order maybe 20, 30 properties that it must satisfy simultaneously. Here I'm showing you sort of a few of these that we screened on. So donor number, which decides whether the salt can be dissolved or not. Camelot-Taft beta, which sort of decides whether you can dissolve the anionic part of the salt. The dipole moment, which decides whether the molecule can rearrange pretty easily. Boiling point, so you want to make sure that the boiling point is much higher than room temperature, so that so that it doesn't boil off into vapor phase. Boiling point is also correlated with the vapor pressure, so you don't want the molecule to vaporize. Melting point is also critical because melting point decides how it performs at low temperature, because as you decrease the temperature, you don't want it to solidify. These sort of molecular levels, highest occupied molecular level, lowest occupied molecular level, tells you what kind of a voltage that you can operate inside. And so what we've done here is we have ordered 400 properties that we have fine-tuned on. And so you can use this in a screening run to be able to screen for all kinds of different attributes. And so here, this is just an example where we're sort of screening on two of these, right? So we're screening on the thermal properties on the gap. And so what we do here is we start with sort of a reference set of molecules. And so the yellow line here is the reference Pareto front, right? A Pareto front is basically, right, when you move in one axis, you necessarily give up in another axis. So here, melting point and boiling point have this sort of Pareto front, where essentially, once you decrease the melting point, right, you necessarily also decrease the boiling point, right? So which essentially sort of, you make it better for low temperature performance, but then you give up some high temperature performance, right? So you sort of have this initial frontier, and the way we do this is we take those molecules, break them up, and then combine them. Then you basically create now a new molecule space, and then we can use MIST to screen over that, and we see that we can basically shift the Pareto frontier. It finds a number of exciting molecules, some of which we are now experimentally validating. The cool thing is you can now take this and then combine this with other models that we have. And we have this old-fashioned model that tells you whether a molecule has an odor or not and what kind of odor. So this is now taking that and then odorless, right? So you can now sort of map the odorless space on top of this. Next, I'm going to tell you a little bit about the journey that we've had in olfaction. Okay, so this, I think, is the clearest proof point of a foundation model. Right? A foundation model is one where one should be able to work on a domain that they know very little about. Right? And so actually, a large portion of this work happened because at last year's SciFM conference in May of 2025, a week before that, right, Karthik, the director at MICDE, Karthik came to me and said, you've given this MIST talk several times, right? It's pretty boring when you show battery electrolytes because you know a lot about battery electrolytes, so it's not clear whether you discovered something interesting or whether the model discovered something interesting, right? Because you know a lot about the domain, and so then it's sort of guided discovery, and so is it really you or is it really the foundation model? And so with a week's time, I asked my graduate student Anushka, right, can we go work on this olfaction problem? Okay, and I was familiar with this olfaction problem because someone had pointed me to this very nice data set and a very nice benchmark that Google DeepMind had put in 2023, which basically curated a very beautiful data set where you had a molecule and you had a set of odors. And of course, it's very challenging because no two people will agree on the odor, right? So they basically served about 15 people and got sort of consensus, and you had sort of an olfactory map. And also, it was good because we had a very good graph neural network baseline, which was built by Google DeepMind. So you could say that, well, that was a good machine learning benchmark on the graph neural network side that we could go after. And why is this interesting? Okay, I'm going to spend a little bit of time telling you why this is an interesting problem. The reason this is interesting is this is a extremely nonlinear problem. And the reason for this is the following. So look at these two molecules at the very top, right? So they look very, very structurally similar, right? So all that has changed is this double bond has shifted from here to here. Okay, so those two molecules look structurally very similar. They're perceptually totally different. One is odorless, the other one is muguet, fresh, floral. Okay? Now you look at these two on the right, they don't look similar at all structurally, but they're perceptually similar, right? So they smell the same. Okay? So you have this sort of so-called discordance problem where you have an anchor molecule and you can change small structural moieties, and the question is, will it then olfactorily be the same or not? Okay, and so it's a very interesting problem statement. Now, it also turns out that, right, this is exciting because, it depends on the reciprocal map, right? So it depends on, who is smelling. And then there's, of course, the exciting thing that there's a very discontinuous relationship between concentration and intensity. So you smell something in a certain way at low concentration and then smell it totally differently at higher concentration. And the other thing that I think is pretty exciting here is this very, very small data set, imbalanced, right, high variance. So it's a very interesting problem. So this is basically, what we did is took the missed embeddings, right, took the DeepMind data set, right, try to fine tune and try to see what we can do from there, okay? And so straight out of the bat, we were able to reproduce essentially all of what they had with a model that was more performant essentially on all of the things. And then I'll show you at the very end where we've done a real challenge problem where its performance improvement is really substantial. What DeepMind showed in their work is the existence of this so-called principal odor map, a POM. And the idea here is you can now naturally see, right, that this chemical space is automatically clustered. So you have the sort of ethereals together, you have the florals together, and you have the meaty together, okay? Now, from this, you can actually create sort of this hierarchical clustering map. This is from our model. So you take the probability distribution of for the output prediction and then try to see the clustering. And what you see here is a natural emergence of various kinds of clusters. So like you can see citrus, lemon, violet together. You have sort of fresh, natural, clean. Odorless is on its own separately. And then you have sort of oil, fatty, waxy, right? Lots of spicy, herbal, warm, right? So there's lots of sort of these features that emerge. And you sort of get this nonlinear behavior that I mentioned earlier. So this is an example where you start with acetone, right? So common solvent, smells nice, right? Ethereal, fruity, etc. You make one change, which is you change the oxygen into sulfur, and you make thioacetone, and then it becomes sulfurous, pungent, onion, garlic, right? So totally different output response, right? And so this is, I think, a very challenging problem because all you do is change one token, and then the output has to be fundamentally different. Okay. Now I'll tell you a little bit about some other examples that we've done, right? So we've done isotopes and organometallics, right? So this is showing that the same model, right? Because the fact that Smirk tokenizer can handle isotopes, right? Can do various things around, right? Nuclear effects, right? So here this is around dominant decay channels into, right, alpha, beta, or stable or spontaneous fission. The right side is things around organometallics, right? So we've only scratched the surface in terms of what we've shown here. Next, what we've done is to go from molecules to mixtures because molecules by themselves are a very small part of space where they are useful. Mixtures are where the exciting stuff is. And the core idea of how we do mixtures is a simple idea, which is that when you mix two things, the dominant part of the mixture is essentially linear mixing. So whatever is the weighted average of the mole fraction. And then all of the sort of nonlinear behavior comes from the so-called excess. Okay? And the excess has to obey some symmetry. And the main symmetry that for a mixture that it has to obey is it has to obey permutation invariance, which is that the label that I give as 1, 2, 3 for the components is totally arbitrary. I could have labeled it as 3, 2, 1. And so if I permute, right, the function representation should have permutation invariance. And so we'd invented this architecture called diff-mix that that gives permutation invariance. And so the idea here is we have molecules, we get the embedding from MIST, and then we use linear mixing to get the linear mixing part, and then we add interactions, and then we can then predict all kinds of properties, right? We can predict densities, mixture enthalpy, and so on. It turns out that the permutation invariant embedding that we end up finding the best performance here is this difference embedding. But this is sort of early days, and there's probably more that can be done here. Okay, so these are some couple of examples. So what we show here is predicting not just the linear part, but the excess part, which is where it's quite exciting. And so what we do here is we predict things that have high excess. Okay, so high excess meaning high nonlinearity. And so this is basically a screening from the model in terms of which molecules will have high excess, and then experimental validation of those indeed having high excess, right? So showing sort of the ability to sort of close the loop. And then this one is a version of that same olfactorily similar, structurally dissimilar map, right? So x-axis is structurally similar. If things are structurally similar, right, then they will mix uniformly, right? So having high excess and structural similarity is, I think, another exciting space to sort of screen over. We can also do things that are sort of much more complicated. This is, I think, where you have sort of physical chemistry meets sort of modern machine learning. So this is sort of transport properties. So you can do, what we do here is we take the embeddings and then predict it through a physical law. Here we use a modified Arrhenius relationship called the VFT, where you predict the prefactor and the activation energy, and then a correction term called the Vogel temperature. And this allows us to now get temperature dependent, concentration dependent transport properties of electrolytes. Okay, in the last about 8 or so minutes that I have, I'm going to tell you a little bit about what we have probed of the model and what we think, what is our current understanding of what it has learned. And so the kinds of things that we've done are we've studied token embeddings. So what do the tokens mean? We've also tried to analyze the hidden states. We've analyzed the sequence embeddings. We've taken the logits, so the output layer, and tried to analyze the logits. We, of course, the part that most people usually care about is predictions and how, what kind of trends do you observe from the predictions. And so, and the other thing that I think we're now pushing forward towards is token attribution, which is given a prediction, right? What token gives you that dominates that particular prediction, and then that allows you to then systematically modify and do guided design. Okay, so this is a little bit about sort of what the token embeddings look like. First, the initial pre-train. So you can think of this as the model's version of the periodic table, right? Basically, how it learns to cluster and put the elements and the sort of submoieties together. So in the initial pre-trained data set, you notice that sort of all the metals and other other sort of both transition metals and other parts are sort of all over the place, and that's because basically in the pre-trained data set, which was done on enamine Rio, there's no transition metals in that data set. Now, once you pre-train on TMQM, which is the transition metal, then you start to learn sort of various things around the transition metal. You see platinum and palladium clustering together. And then you have osmium, ruthenium, molybdenum. So you sort of start to see the D block cluster together, various other things. You start to see this nitrogen, oxygen, phosphorus, sulfur, bromine, fluorine cluster together. In this free sol data set, right, you have this sort of very nice silicon, phosphorus, nitrogen, oxygen, sulfur, bromine, fluorine, right? So you start to see it's self-learning, right, the elements of the periodic table. Next, we try to see whether it self-learns aromaticity, which is basically the ability for a molecule. Aromaticity is a very, very tricky property because it depends on how many pi electrons does that molecule have. It's a very subtle feature because if you have 4n pi electrons, right, then it's anti-aromatic. If it has 4n plus 2 pi electrons, it's aromatic. Okay, benzene has 6 pi electrons, so it's aromatic, right, versus cyclobutadiene, which is 4 pi electrons, anti-aromatic. Okay, so you start to see naturally, right, this clustering where it learns between anti-aromatic and aromatic directly from the sequence embeddings. It also is able to learn catacondensed and pericondensed, which is when you have these aromatic rings, do they condense in a chain or do they condense in sort of these cages, right? And it automatically sort of self-learns, right, this condensation behavior. It's also able to sort of discover trends, right? So you now have a problem where you have a functional group and then you extend the chain length and then you try to see what happens. This is fairly trivial for chemical properties because what happens is after a certain point it just will saturate because it doesn't matter what the functional group is. If you have enough carbons, right, the carbon dominates the thing. But this actually turns out to be an interesting one for olfaction because as you extend the chain, there's a sudden phase transition. So if you have an aldehyde, right, at the beginning it smells sort of fruity and green and so on, and then at a certain point, right, in this case, when the carbon ring carbon chain goes above 11, it goes to sort of this waxy floral state. For carboxylic acids, that number is sort of at this 9 point, where it again changes into sort of this fatty, waxy side. Last bit is sort of trying to do this token embeddings and then doing token attribution. And so the idea of token attribution is, given a particular molecule, which part of that molecule gives you that particular property. Okay? And so here, for example, right, this is a molecule, and we ask the question, what makes it smell like sulfur? Right? And the token attribution says that sulfur makes it smell like sulfur. Okay? All right. Now that's obvious, but now we'll do something non-obvious, right? What makes it smell sweet, right? And it turns out that this ester group is what makes it smell sweet. Okay. This, once I saw this one particular example, this is when I really saw the power of a foundation model. Okay. And this problem statement is very, very interesting. Okay. So focus on these two molecules at the top and these two molecules at the bottom, right? Notice that basically the left side is essentially the same, with this being an ester and this being an alcohol. Everything else is the same. And the change that I'm going to do is just add this methyl group here. And what you have in one case is no change in smell, right? You get the olfactory profile that is the exact same. And then on the right, you get basically a transition from muguet to sandalwood. And what the model does is it correctly says that the addition of this methyl group, all the token attribution actually shifts to that methyl group. And that's why there's a change from this case, and this case, there's no change. Which actually shows the sort of power of this model. And the last example that I want to show you is, this is, I think, the most powerful demonstration of what we have been able to do so far. This is the so-called discordance problem. And so the discordance problem is, you have an anchor molecule, and then you make two changes. One is you make a change which is structurally similar, right? So here you take this molecule, and then instead of this being a carbon, you substitute that to be nitrogen. So these two are structurally similar, but olfactorily dissimilar, right? This smells fishy, fruity. And then here, you have a completely different structural cliff, but they're olfactorily similar. This smells like apple, this also smells like apple. And so it turns out that this is a very difficult problem. The best DeepMind model, with DeepMind then spun out a company called Osmo, but this is the best model that they have. And humans can do this discordance problem at a rate of about 90.4%. The best machine learning model to date can do about 50%. And our discordance labeling from the missed embeddings is about 62%. So this is a dramatic improvement. It's over 25% improvement from the state of the art. The last bit is, we've now chained this with sort of standard LLM. So this, you can use tool use, and then you can do all kinds of fun things, right? So this time, I'm not going to do a live demo, but this is one thing that my students always like to do, right? Which is they now can do, their favorite problem. Here they're designing an aviation battery electrolyte that also smells nice. And I think, I forget what it finds, but I think it probably finds like some fluorinated molecule that has a nice smell. And so it does this trifluorinated DMC, which has a fruity, sweet, tropical smell. So with that, I'll close. This was a monstrous amount of work. About 25 people worked on this paper. We had massive amount of compute resources from DOE Insight. We had a 2024, 2025, 2026 Insight Award, National AI Research Resource Pilot. We were one of the first to get onboarded, and NVIDIA, who gave us DGX cloud access, and Argonne for sort of all the support with getting our compute and scaling done. And then Los Alamos for funding our Los Alamos collaboration for funding a large portion of this work. And thank you for your attention. Happy to take questions.
So here I'm having a first question from the Pigeonhole, and it's, why do you believe your data is redundant?
Yeah, so we didn't know it, right? So if we knew it, we would have been smart about it. So what we see from our analysis of the scaling laws is that the scaling law exponent, alpha, right, comes out to be higher than beta, which is an indication that there's some redundancy in the data set, that we could have basically pruned our data set and taken a smaller data set and gotten similar model performance. Which of course, would have given us a better, we would have been able to be more computationally efficient. So this is not something we knew, right? This is the observation. There's very little known um, about the quality of the data sets and how well they do in both pre-training and then sort of fine-tune model performance. So this is, I think, an open area of research. But I think this is what we observed.
Great, thank you. And the next question is, as you showed very interesting findings with the smell. So one of our audience is asking, can this be applied to the sound domain, like similar to the chemistry domain? Like, can this type of model to apply to basically either listen to the sound or like, instead of doing like the smell?
That's interesting. Uh, Usually, we get the smell and taste question. We don't get the smell and the sound question. So this is very interesting. Uh, I Yeah, I would have to think about it. I don't know how. Yeah, it's a great question. It's some homework to do for me.
And we have a question.
Yep, please.
Curious about stress testing the model, like were proteins in the data set, and then if you try to predict some behavior of proteins, like how does it break down or does it work?
Yeah. Um, so I think this is exactly what we are trying, right? Various kinds of ways in which we want to see the model fail, and then we try to fix it. We have not done any protein-related tasks, um, but what we have done um, that is maybe close to that is we've started to probe organometallics uh, quite strongly, where a lot of the similar kinds of features that sort of are important in proteins emerge, right? Which is sort of these 3D distances, sort of far away, right, become important. Um, what we do find is that um, it does pretty well, surprisingly, right, for the organometallics, which we thought it would sort of fail because there's a lot of 3D information, and um, and I think some of that has to do with the fact that the attention that it learns has some inherent sort of three-dimensional information. So if you look at the attention map and what it perceives as, if you sort of did some sort of an inverse distance map, it's able to find that the obvious thing, right, is in a 1D string representation, right, what is closest to you to the left, right, is the ones that are that you should pay attention to, right? But the interesting stuff is, right, there's a token far away, but far away in sort of the 1D sequence, but then close in sort of three-dimensional geometry, right? That sort of becomes important. So we see that it's able to learn those kinds of attributes. Um, Now we do know that there are various ways in which I think it could start to sort of struggle. Um, and no, I think stress testing it is, I think, the direction that we're going, where it hasn't seen any like F block chemistry at all, right? So for example, what would happen if if we gave it F block chemistry, right? So is it just a continuum, right? That we think of it as F block chemistry, but maybe it's just a continuum from S, P, D, and then F is just a natural continuation. If that is true, right, then that actually creates a fundamental foundational concern, right? That we sort of think of lanthanides, or like the so-called nuclear elements, right, as a different class of different behavior, right, than what happens before that, right? There's sort of z equals something till something is all sort of everything is nice and great, and we can study about it all in completely open, and then like after a certain point not, right? But if the model is able to sort of easily generalize, right, to these sort of unknown z's, right, then I think that's very, very interesting. And I think these are the kinds of open questions that we're trying to probe. And we'd love, I mean, the model will be open source, so we welcome other people to try things about this. So thanks.
We have a question on the left side.
Can you hear me?
I'll repeat it. Don't worry.
Yes. Thanks so much for the presentation. My question is that from what I see, like, did you like train your model on 1D representation of molecules? Like, did you try to train it on the image of molecules, for example, 2D, or in on the 3D structure like X, Y, and Z files, that stuff? Or is this just for 1D representation like smiles or smirk or whatever?
Yeah. So all the pre-training is done only on the 1D string representation. So there is no 2D, I mean, technically it's 2D in a sense because it has sort of the structure information, so it's sort of a 2D structure in a sense. But we don't have any 3D geometry information, right? I think that's what sort of you're getting at. So we don't have any 3D structure information in the pre-training of MIST. Now we do try to we do so that's why when I said it was sort of state of the art across a number of benchmarks, right? It's obviously very, very good on benchmarks that don't explicitly require the 3D coordinate, right? So on all benchmark, I mean, there's a bunch of QM9 benchmarks, so bunch of quantum mechanical benchmarks that don't explicitly, need that geometry information, but there are some things that explicitly need geometry information, where certainly, right, some of the geometry-based equivariant models do perform better. For example, right, things like dipole moment and so on, dipole moment polarizability, which all require sort of the geometry much more intimately, right, end up requiring the 3D coordinates does help you. But for these kinds of for most of the tasks that we sort of end up needing in sort of real use cases, what the property we have is a collective property, right? So like boiling point, melting point, blah blah blah. So those properties, right, end up not, the 3D geometry doesn't actually help you, and having a large corpus of unlabeled data does help us, right? So now I think there's an exciting direction where you can combine all of these things, right? Where there's obviously 3D geometry information. So can we combine our 1D string representation with this 3D geometry? And the challenge there is around sort of obviously, multimodal, right, is a way to go, right? But I think the challenge with multimodality is aligning the representations from these modalities. And so that's an open question.
I just have second question. Is that okay? Okay, so my second question, can you return back to the slide where you have Mistral benchmark for 10 billion or 1 billion? So sorry. So there's a slide show like Kimbert, Mistral 10.
Yep. Yeah, you're going to ask me where did we land? Is that on the color code? Is that the question, or?
Like 10 billion, this is molecules generated, or this is like tokens? This is, and if this compound generated, this is like compound is already known like in amine one, or like it's virtual novel one?
Yeah. So the molecules that we pre-trained on are molecules that are actually a subset of enamine real. So they basically are real molecules that can be that is synthetically accessible. This is not a virtual library. So this is based on molecules that are known to be made. And all of these models are trained on different kinds of various kinds of these kinds of data sets.
size of training or the same as training?
You mean so you mean what kind of molecules are in the?
Yeah, so let's say you train it on enamine.
Oh, yeah, yeah, yeah. Oh, great question. Yeah, so most tasks end up having. Um, okay, so I think the question you're asking is are the prediction tasks in distribution of your pre-training task, right? So no, most problems, the molecules and the materials that we study are totally out of distribution of the enamine Rio. And the easiest way you can see this, right, is we do very well on this organometallic data set. An organometallic data set has never, I mean, the pre-trained model has never seen a transition metal at all. It has certainly seen complexes, right, but it's never seen a transition, most of the transition metal. And then when you give it TMQM, it's able to learn it very quickly.
Yes, we'll have our time. We'll have the time for our last question, and this is like a bit long question, so please bear with me. So, is this all based on the belief that our understanding of molecular bonds are complete and accurate? What if there are unknown new moleculars and the molecular mechanisms?
Okay, amazing question. So this is, I think, the core question. Can it learn? So from all that it has learned, can it learn something that is totally, totally new and totally unknown, right? So, and I think it's an open question. I think the the current my current thinking on this is that it is able to do highly challenging tasks from a human perspective. Now it might be that from a in its latent space, it's an obvious task, and we just don't think in that latent space. So I think it is to be determined, right? Whether, I think this is a open question. Can it like basically completely change sort of the chemistry rules and sort of do something totally novel? I think this is something that we should explore, and maybe the next time I give a talk in this auditorium, I'll have an
Great.
answer.
A quick follow-up is that if a model is demonstrating like struggling at a point, does that mean that maybe there are something like innovative that's hiding there to discover?
Yeah, I mean everywhere it fails, right? There's some gap in either tokenization, representation, or there's some hidden variable that you're missing, right? So I think that's why we love finding out where our model fails, right? That's when you learn a lot. So
Great. So let's thank Venkat again for the great talk.